So let's just jump right into the topic. The first motivating example is essentially finding a path, an optimal path in a polygonal environment. And we all know that the optimal path lies in the visibility graph in this situation, which means that the optimal path comes really close to the obstacles that are present in the environment. And in reality, like just to avoid any possible constraint violations or collisions with the obstacles, we kind of perturb the trajectories around these obstacles just to make sure that we satisfy the collision constraints. But the question exists, the moment you perturb these trajectories, you lose optimality. And the question here is there a way to kind of do it in a principled way, so that you're sure about your suboptimality or the trade-off that you're having in terms of optimality when you perturb for your constraint violations, or you can call safety. With that motivating example, I would kind of move into this idea of, let's say, under the situations where the obstacles are also kind of uncertain. And the thing is, you plan for a kind of environment, but then the environment is dynamic and uncertain. And how do you ensure that the constraint violations are reduced in this sort of uncertain environments? And if you look at the literature, the most popular set of methods assume that the uncertainties are stochastic, and methods using Gaussian processes, POMDPs are prevalent. I mean, there's a lot of work in this regard. But in this work, we kind of take a fundamental different approach where we assume that the uncertainties are parametric of nature, which means that the model parameters in the system have some nominal values that are available to the designer, and the parameters assume variations around these nominal values. And with this assumption, what I'm able to do is I can come up with a simple deterministic optimal control formulation for the original problem without going into this stochastic realm that kind of makes it easier. And you will see that in a while. And this also gives us solutions that can address limited feedback capabilities, where, for example, if you have input saturations or feedback constraints and, let's say, limited sensing, where you want safe open loop trajectories. And we'll see this in a second. But the idea is essentially, how do we capture variations in your trajectory or in your solution under parametric uncertainties? And that's the question we have. So let's say the dynamics of the system is given by this ODE, where X represents the state, T is time, obviously, and U is the control, and P here represents the vector of uncertain system parameters, and I assume P0 is the nominal value that is available to me. So given the system, let's say I have the initial condition T0, X0 at T0, and if I plug in the nominal value of the parameter for some control input, and I propagate this system with the above dynamics, I can get what is called the nominal trajectory. Now, let's say you assume some variation around the nominal parameter by, say, delta P, and for the same set of control inputs, if you propagate the system, you get what is called the perturb trajectory. Now, at some time T, I can figure out what is the variation in the state by essentially comparing these two trajectories, and I can talk about variations of state at each and every instant of time. So if you want to automate this process, I can define what is called sensitivity function that captures variation in the state up to first order, for example, variations in the parameter. And as you may notice, the sensitivity function is also a function of time, obviously, because you are looking at variations at every instant of time for the given parametric variation. And the interesting thing is you can define dynamics for the sensitivity function, and surprisingly, it's linear. So you can see here the A and B matrices are the Jacobians of the dynamics. I'm sorry about that. The Jacobian of the dynamics are the nominal conditions with respect to state and the parameter. And also notice that the initial conditions of the sensitivity function is 0. What it states is the initial condition x0 does not depend on parameters, which is obvious. And in this case, since we are assuming that the initial condition is also fixed, you can say safely that the variation in the initial state with respect to parameter is 0, which is why the sensitivity function at the initial time is 0. Actually, this sensitivity function-based dynamics is already existing in literature. I mean, you can check Khalil, for example, where he calls it a sensitivity equation. So now that we can talk about variations in the state or the system with respect to parametric variations using these sensitivity functions, how do we utilize these sensitivity functions to talk about planning under uncertainty? And one idea is trajectory desensitization, but before I get into that, let me just introduce some notation to the problem or the subsequent problems that I'm going to discuss in this presentation. So we'll be dealing with optimal control problems. So here is a standard optimal control formulation. You have your cost. There are two terms that are standard, which is the terminal cost represented using phi at x at tf, comma tf. And then there is a running cost that goes from t0 to tf using an integral cost. And you can define the dynamics for the system, the same dynamics that I had presented in the previous slide with the initial condition. And here there are a bunch of constraints. The first set of constraints are essentially the state constraints or trajectory constraints given by g of x at t, comma p, comma t less than or equal to 0. And you have a terminal condition, like let's say in the case where the final time is not fixed, you need to have a terminal condition to stop your optimizer. And that is given by psi at x at tf, comma tf equal to 0. And again, as I mentioned, p naught is the nominal value of the uncertain parameter p. And this setup can talk about optimal planning and decision making for a wide range of problems. Say, for example, let's say even planning, optimal path planning in a dynamic uncertain environment where the environment has moving obstacles, or for example, even systems that are as complicated as hypersonic vehicles. So, okay, we have the optimal control setup, and let's move into this idea of trajectory desensitization. So what I did here is I just took the set of equations that I had presented in the previous slide, and I just plugged in the nominal value for the parameter. And if I solve the problem here, what I get is essentially the nominal solution for the optimal control problem. And I call this the original optimal control formulation under nominal conditions. And say you solve this problem under the nominal conditions using an off-the-shelf solver and you get the trajectory. Now under parametric variations, you realize that the trajectory is dispersed, and say this is the amount of dispersion that you get. The idea is, can we reduce this dispersion and track the nominal? The most traditional way to do that is essentially using a feedback controller. So essentially what it does is you are tracking the nominal based on the variation that you see at every instant of time, and you have some sort of gains that would try to bring you back to the nominal trajectory. But if you think about it, a feedback controller has limitations, and it can, under really large variations, the feedback controller can get into input saturations, and there is nothing much you can do in terms of tracking the nominal, and you might end up having these sort of high dispersions that are not really acceptable. So one way to do that is essentially, can we change the nominal so that the feedback doesn't take all the responsibility of tracking the nominal? Essentially, trade off your nominal optimality so that you can be sure about your feedback performance. And to that end, we can come up with this augmented system where you now introduce a regularizer in the cost that is based on sensitivity function. Here, since the sensitivity function is a Jacobian, essentially it's a partial of your state with respect to a vector of uncertain parameters. It is a matrix. So I just use a vec operator there. And you can actually weigh in the values of the sensitivity matrix that talk about the variations that you would expect under parametric variations with some weight matrix Q that could be time varying. And to capture the regularizer, you need to augment the dynamics of the sensitivity function, or essentially the sensitivity equation, and the set of initial conditions for the sensitivity function. And what I claim here is essentially this modified optimal control formulation would reduce the variations in the trajectory in open loop scenario, which would essentially help in the feedback situation by reducing the effort for the feedback controller. Again, in the same way, let's say if I'm not interested in the entire trajectory dispersion, but let's say I'm only interested in the dispersion at a particular time, let's say the final time. So to that end, you can again modify the regularizer by just penalizing the sensitivity at just the final time. And of course, the augmented model and the initial conditions remain the same. So let's look at some examples to understand this idea. This is a standard time optimal Zermelos problem. So what's happening here is, consider this boat that is at the origin on the shore that is essentially the x1 axis, and it has to reach some point on the shore 2, 0 in minimum time. Okay, and then there is this flow that can assist you kind of to reach that point faster, but the flow is uncertain. And I'm capturing the flow using this function p of x2, p times x2. What it means is the flow is parallel to the x1 axis, and it kind of increases in intensity as you go away from the shore. And that is the weight increases is linearly with respect to the distance between the shore and the point along the x2 axis. So in this example, I'm assuming the slope with which the flow increases as the uncertain parameter, and I'm assuming the boat has heading control with constant speed. Now, if I want to assure that I can reach the final point with high amount of precision, which means reducing variations in the final state with respect to variations in the flow, I can penalize the sensitivities, and I can define the sensitivity function as I had expressed in the previous set of slides using sensitivity equation, and I can penalize the sensitivities using this now a simple weight calling alpha, which means if alpha equal to 0, then there is no what I call is desensitization or penalization of sensitivities. And then as you keep increasing alpha, you can see, for example, for the plot on the left, where the trajectory becomes more and more conservative. It is moving towards the shore, which means it is trying to reduce the variations by not going too much into the flow that can perturb the final state a lot. And that is also captured by the plot in the middle, where you can actually see a period of frontier. The y-axis represents the sensitivity at the final time, or actually the entire time, and you can actually see the period of frontier by looking at the final time plot with respect to the flow uncertainty. And again, you can see that as you keep increasing alpha, your travel time is increasing, but at the same time, you're reducing the dispersion in the final state. Again, that is established by the Monte Carlo simulations on the right. Here, I think I took almost, 100 or 500 samples. I don't remember the exact number, but again, it is very clear in the plot. This is with respect to Zermelo's problem, and the most recent example that I had tested this idea of trajectory desensitization is in the hypersonic vehicle regime. So here the hypersonic vehicle is essentially an X-33 model, which is an experimental vehicle. And I'm simulating here a situation where the vehicle is entering the atmosphere, I think roughly around 12 kilometers from the Earth's surface, and it wants somewhere in the Pacific, and it wants to reach the Kennedy Space Center in minimum time. Here you can see the entry and the terminal points on the plot on the left. And what I'm trying to do here is, while I want to reach the Kennedy Space Center in minimum time, I am concerned about the dispersion in the final position with respect to variations in atmosphere and aerodynamic coefficients. Here particularly, I looked at atmospheric variations in terms of the scale height, essentially that captures the rate at which the density reduces as you go in higher altitudes. And CD0 essentially is the drag parameter that I assume is uncertain. And you can see here that the moment I have the desensitization kind of plugged in with respect to baseline, which has no desensitization, you realize that the error ellipse is kind of reduced by almost 70 to 80%. Without a desensitization, you can see the variation in the final position to be as much as, like, let's say 53 kilometers. But the moment you try to impose this desensitization regularizer on the problem, you can see the dispersion under the parametric variations reduced to almost 7 kilometers. In this problem, I also penalized variations in energy because for most aerospace applications, the variations in energies can lead to dire consequences. You want to make sure that at a particular height, you have a particular amount of speed that kind of keeps the energy within acceptable limitations. Again, on the right, you can see this energy error in terms of probability distribution. And in this case, you can see that in the desensitized case, the tails are reducing. The tails for the energy error decay pretty fast, and you can see this big peak at around 0 energy error, essentially establishing the fact that you are reducing the energy error dispersion under these parametric variations in scale height and drag parameter. So these are some of the new results which haven't been published and which will come next year. And if you're interested, you can keep following this space in the realm of aerospace solutions. We are looking at Aero Capture also, which is one very sensitive maneuver that happens for spacecrafts, for example. So moving on, I mean, till now we had seen dispersions in, let's say, the entire trajectory, or let's say a particular state with respect to parameter variations. But what about constraint violations? I mean, just because you reduce variations in the trajectory doesn't necessarily mean that you are reducing variations in the constraint, or essentially the constraint violations. And we are now focusing on the constraint function, which is g of x comma p comma t. So if you take the previous approach where you just look at the variations in the trajectory, you can also look at variations in the constraint by calling what is called constraint sensitivity, and you realize that that is also a function of the sensitivity function that we had defined earlier. So the question now is, just like the way we had penalized the sensitivity function to reduce variations in the trajectory, or let's say state at particular time, what if I just penalize the constraint sensitivity and just reduce the constraint sensitivity? Let's explore this idea a little bit with a simple example problem first. Consider the situation. So you have the constraint boundary, and to the left is the feasible region, and to the right is the infeasible region. And I pick 2 points in the feasible region, point 1 and point 2. So point 1 is further away from the constraint boundary, and point 2 is closer to the constraint boundary. And the circles around the points represent the magnitude of the constraint sensitivity around that point. And you can quickly realize that if the point is further away from the constraint boundary, even large variations in the constraint doesn't really result in a constraint violation per se. But if the point is closer to the constraint boundary, even small variations in constraint value can lead to constraint violations. So which means constraint variations are more likely to cause constraint variations are more likely to cause constraint violations when the system is closer to the boundary. So if you penalize just the constraint sensitivity, it might not work. And to this end, we define what is called relevant constraint sensitivity, where we weigh constraint variations as a function of the constraint value. And we introduce what is called relevance function. And in this set of work, the candidate relevant function is the derivative of the logistic function. So if you look at the logistic function's derivative, you can see that it has this bell-shaped structure with decaying tails. So which means if 0 is the value for the constraint that you see at a point, that's where you have the maximum relevance, because as you come closer to the constraint boundary, you want to be sure that those constraint variations are weighed in more. And if you are going further away from the constraint boundary, those variations matter less. And in this case, we are looking at an exponential decay of those for the relevance of those variations. And we define RCS as a function, as a product of both the relevance function and the constraint sensitivity. And we penalize this particular constraint sensitivity to arrive at conservative trajectories that ensure less number of constraint violations under parametric uncertainties. So let's look at experiments in this case. The experiments that I had conducted essentially are for a 2D time optimal path planning problem. We assume that the agent has constant speed with heading control, and all the obstacles are identical and move parallel to y-axis just for the sake of simplicity in implementation. And here I assume that the obstacle speeds are the uncertain parameters. And the constraint violation function is defined using the Euclidean distance, which you can see here, between the agent and each obstacle, and R0 is the safe distance between the agent and obstacle. So before we get into the experiments, I just want to discuss the idea of relevant constraint sensitivity and why it is important using these two set of plots. While I claim relevant constraint sensitivity captures this idea of whether the constraint variations matter or not, but we can see that using a plot here. In this case, for this particular set of experiments, we can arrive at the constraint sensitivity in closed form without actually using the constraint function in its dynamics. The expression can be seen at the bottom left below the first plot, and to the left is the constraint sensitivity and to the right is the relevant constraint sensitivity. And you can quickly realize that in the relevant constraint sensitivity, the value of RCS is more prominent around the obstacle, while in the constraint sensitivity, the constraint, because you are looking at just the constraint sensitivity alone, its value doesn't really depend on the position of the agent with respect to the obstacle, and this can have some interesting this can lead to some interesting phenomena which you will see in the next slide. So here are the optimal trajectories that I obtain by just penalizing the relevant constraint sensitivity along with while I optimize for the time travel. And you can quickly see that as I keep increasing the penalty on the RCS, you will see the trajectories become more and more conservative, where black being the most desensitized in this case, with longer route but being further away from the obstacle. And on the right, you can see the plots for RCS and constraint sensitivity. Again, if you see RCS plots, as you increase weight on the RCS penalty, you will realize that the graph under the corresponding RCS plot is reduced. And interestingly, for this particular example, the constraint sensitivity becomes higher and higher for the conservative trajectories, which means if you just penalize constraint sensitivity for this particular example, you won't arrive at these sort of conservative trajectories, which is, again, something that I want you to note. This is just a simple example with just one obstacle. And you can look at a case where there are 10 obstacles. And again, the penalty on the RCS involve longer trajectories, but being further away from the obstacles. Just because, again, the obstacle speeds are uncertain, which means if you're closer to the obstacle, you can experience constraint violations. So on the right, I capture the trade-off plots. Again, on the topmost, the right top plot essentially captures the collision probability versus weight on the RCS penalty. And you can realize that the moment I kick in alpha, which becomes non-zero, you'll realize that there is a sharp decrease in the collision probability with acceptable increase in travel time, which is captured in the plot below. So this is for a multiple obstacle case. We tried for different other number of obstacles, and the result is the same, where again you would see longer trajectories, but less number of constraint violations in all these cases. One interesting observation for this set of experiments is essentially the dependency on the constraint form. What I am essentially trying to point out is the moment I change the constraint form from, let's say, Euclidean distance to some other norm of this form, where lambda here can be anything greater than 0, and that is still a valid constraint form, you will realize that for different values of lambda, the corresponding RCS plots are different. For lambda equal to 0, lambda equal to 2, lambda equal to 4 are the plot that I've shown here. For lambda equal to 1, you essentially recover the Euclidean distance. And you'll see that the corresponding trajectories for those RCS plots have different curvature, which means here lambda could be some sort of hyperparameter that can be tuned for the desired curvature that you want for the trajectory to obtain. Again, this is kind of interesting case where you cannot just blindly take any constraint form and assume that we can obtain this sort of conservative trajectories. And to essentially stress more on this point, we had come up with this experiment, what we call car versus train problem. The idea is essentially there is a car and it wants to reach the target point on the other side of the rail track by essentially avoiding collision with the train. And again, we assume that the speed of the train is uncertain, and the agent can control its speed with a bound on the maximum speed. And again, if you assume the constraint form to be of Euclidean nature, you won't end up with the conservative trajectories, which is what we had found from the experiments, because the driver doesn't really consider the collision avoidance in this form of Euclidean constraint. Imagine if the driver is not on the track, it doesn't really matter whether the train is doesn't really matter where the train is. Only if he's on the track, he wants to make sure that there is enough distance between the train and the car. So to essentially capture that idea, we modify the constraint function using an using what is called this boxcar function, or let's say an identity function. It essentially captures the idea of only if you are on the rail track, you want to maintain sufficient distance, but everywhere else the constraint is null. And essentially the boxcar function in this case is non-differentiable, so we essentially use the so-called super Gaussian approximation for the constraint to be differentiable. And in this case, the moment you construct the RCS using this modified constraint form and penalize the relevant constraint sensitivity, you realize that the conservative trajectories now maintain enough distance from the train while crossing the track. Again, this emphasizes upon the fact that the appropriate constraint function is a must when you design these sort of trajectories. So with that, I want to just conclude quickly by saying that we looked at a sensitivity function-based regularizer to address safe planning under parametric uncertainties. We had looked at trajectory desensitization, final state desensitization. Particularly for the constraint desensitization, we looked at relevance functions to address constraint violations under parametric uncertainties. So our future work essentially involves looking at game theoretic formulations where there is asymmetric information between the agents. In this case, let's say we are considering a pursuit evasion game where the evader has the exact information of the parameter where the pursuer is at an information disadvantage. And we want to figure out what sort of trajectories can we design based on this idea of desensitization. With that, I would like to thank my collaborators. Actually, I collaborated with Merrigan and Jack on the trajectory desensitization part, and Hemant and Vino helped me with the constraint desensitization. And Professor Siothris and Professor Hutchinson have been very grateful, have been guiding me throughout this project, for which I'm really grateful. Yeah, with that, I end my presentation and I'm open for questions.